So now we're going to design inside FEKO this the directional coupler based on coupled lines. We just created some variables here. For instance, this is the thickness of the substrate, H. This is the length of the line, of the coupled line, which comes from here, 8 millimeters, right? This is the length, this length here. What else? S is the gap between both lines. It comes from this thing here. It was designed here, it was 0.208. What else? W50, which is the length, which is the width of a 50 ohm line. And basically you create these variables, just variables, right click, add variables. You add a dielectric. You just, instead of creating something new, you just go to media library and type in FR4, and then we can proceed with the geometry. We give it a name and we start designing the rectangle. We select this option here just to make it centered. This is supposed to be W and this is supposed to be L. This is add. We don't see anything. We just go to F5, right? F5 here. First thing, we translate this piece here from zero, from the origin to S plus W over 2. Here we type in 0. Okay. And now we create the other line. We just make select here, copy and mirror, and we just select this thing here. Okay, just to check, tools, Ctrl Shift from here to here, 0.208, which is the desired distance. In our case, we are going to get this 450 ohm lines over here. So how we do that? We just make another construct with Tangle. Here we are going to use, for instance, W50 and L. It's too big. L over 4, L over 2. I guess that's all right. And you create, let's change it just to make it simple. L over 2 and W50. Create. And now we can move this thing here. So transform. So we have to translate this thing here. So from this middle point here to this extreme, this corner here. Now we have our 50 ohm line. It's easier just to keep it selected. Copy and mirror. We just play with the work plane till it's something like that. Okay, with both selected, we don't waste our time. Copy and mirror, and again we just play with the work plane so we see the other two here. Okay, now we have almost everything done. We just need to close these things here. The microwaves, they don't like these transitions, this sharp edges. So we are going to do this. Let's go to construct a polygon, and you are going to select the points here using Ctrl Shift. So Ctrl Shift from here to here to here. Create. Done. We could do the same on the other points, but I think it's easier just to keep it selected and go into transform, copy and mirror. Here we play with the working plane. There we go, you see here. Both pieces selected, we go again to copy and mirror. And now we play with the working plane, not this, not this. There we go, you see them here, the ghosts. Okay, now we have almost everything here. We just need to create what? The substrate. The substrate is a little bit tricky depending on the way you define your coordinates. But we go to construct, cuboid, and now I'm just deleting these things here, which is our W. Our W is along the X, along the U, and our D is this thing here. You just type everything here, you don't care. We just inform the height, which is our variable called age, just checking. Age is 1 millimeter. Create, there we go. We say that this region is right click, actually the substrate, FR4, we change the material. And now another tricky part, we have to make it a little bit larger. You see, it's touching the edges of the transmission line. This is not good. We come back here and we identify, I guess this is this variable, if I'm not wrong, 1 millimeter more. Actually, it's minus 1 millimeter. It's a little bit larger. You can see the ghost image. We can put it 2 millimeters. I guess that's cool. Just for the sake of following the procedure, the workflow, we don't care that much about the result. And now we can do something a little bit tricky, which is the ports. So to do the ports, pay attention to the workflow. I think it's easier if you just hide the substrate. And now we can place the working plane here. Work planes, right click, add work plane, Ctrl Shift, something like this. You click here, all right. Oh, I forgot something. I have to set it as default. Now it's gonna work. Now it's gonna work. The U is W, it's H, and here is W50. Right? Do something like that. Create. You are going to, with this thing selected, transform, copy, and rotate. Set it to be 90. Switch the work plane till you have something like this. Something like this. It's all right. Then you take this thing here, just this vertical piece of metal, and you go to translate, Ctrl Shift from here, Ctrl Shift here. There we go. Next step, you select this thing here, again, copy and translate. Ctrl Shift from this point here to this point here. We're almost done. I guess that's the port. Next, you select this vertical sheet, and for this vertical sheet, we go to work planes, add work plane, and with Ctrl Shift, you select this middle point on this face. Create. Right click, set as default, and for this case what you're going to do, we go to construct and split. We are going to take this grid this working plane as a knife, as a blade. We need to switch till you see something like that. We just type in create. We have two halves here. We just type in union. That's our port. So then we select the union and these two rectangles, and we do the same. We transform, copy and mirror. Oops, we have just to go back to work plane and select the global plane to be the default. Now we can proceed. Union, this guys here that you just created. This is our port. Copy and mirror. We just change the work plane. You see it? It shows up on the other leg. Keep it everything selected, and again copy and mirror. Now we flip the working plane till you see them here. You see? Okay. Now we have all the ports, and these unions, they are supposed to be our edge ports. FEKO calls them edge ports. So first thing, you go to this thing here, you select these two rectangles, and we go to source load, edge port. Nothing is shown because we have to select them faces here, edge ports. Let's take as a default the port, the lowest port is the negative. There we go. You move to negative. We created our first part. Here we do the same here. Select both faces. Edge port, the yellow one, we move to negative. Port number 2, we rotate it. Select again here. Edge port, the yellow one, we move to negative. And finally, select them both, edge port, move to negative, create. I think almost everything is done. We make visible again our cuboid, show height. We toggle the visibility of this piece. And now the final thing, if we haven't forgotten anything, we just select everything, all the objects, they got to be selected here, so you can use the union operation to tell FEKO that all of them are physically connected, right? This is a little bit tricky. We have to tell FEKO which faces are metal, just checking. For instance, this is the ground plane. You see it's yellow over here. I make it bigger here. This is the yellow. This is the ground plane, so I right click, properties. I tell FEKO, hey, this is a PEC, apply. What else is metal? You just need to check on your F5. It says this thing here is metal, this thing here is metal. This is all this line, all these faces here, they have to be set as metal. Here, 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 I'm just selecting all of them. All of these guys, they are PEC, right? What else? These guys are metal, metal, metal. You just go through the objects on your case, just check them if they are all alright. PEC. Who is not PEC? This face here. A tricky way, we just right click and go to zoom to selection, and then you can see where this part is located. Here is this thing here, 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 here must be the lateral, the side view. As yeah, this is not supposed to be PC. Okay, I guess it's everything. Right, and finally this thing. The modeling is done. F5. We need to tell FEKO that we are covering the frequency of our design is supposed to be operating at 5 gigahertz, from 10 gigahertz all the way to 7 gigahertz. Let's say we have 21 points. It's very fast. Let's increase it to 42, 41. And next thing, we just have to request, and under configuration, we go to request multi-port S parameters. We add 3 more ports, port 1, port 2, port 3, and port 4. Is going to be to be considered as an S parameter simulation. I guess that's basically everything. We just can then solve. We need to mesh. The simulation will run with the method of moments, and it's very fast. Done. We can go now to post FEKO, and then there we can analyze our results. We type in Cartesian, and you just drag and drop this request here. This is our S11. We can see this is way too fat here, just reducing this thing here. You can see that our S11 is below 10 dB, sounds cool, sounds nice. We can add another curve. Let's call it this time, just going to the port numbering. If I'm not mistaken, port number 1 is here, and we have to see the coupling with port number 3. Yeah, that means S31. We go to the second curve, and you ask to see S31. It has to be more or less 10 dBs, exactly at 5 gigahertz, right? You can see that it's more or less fine. And another curve, just drag and drop another curve. This time we are going to ask S41. S41 has to be as low as possible. You see, the red one is S41, is this below more or less 10 dBs. And finally, S41, going back here, is you excite here, and you are not supposed to measure anything here. It should be more or less minus 100 dBs in the best case, but it's very hard to get it in the real world. And finally, the S21, which is the power that goes through the line, has to be a very low number, close to 0 dB. Just check. S21. Here, you see it's close to 0 dB. So this is more or less the simulation. Just for the sake of improving the results, if you want to check later, we can use with CAD FEKO. So to make the point refinement, the polyline refinement, we can say that, for instance, with Ctrl Shift, we select only the gap. This is a very tricky thing to be done. Create, right? And this polyline refinement, we can say, for instance, that our radius is supposed to be 1 millimeter, and our mesh size, for instance, 1/10 of a millimeter. Something like this. And what FEKO is going to perform, the mesh is going to be finer here. You see? Now we can run the simulation again. Why have I done this? Because I know that from experience, from the theory, that one of the most sensitive parts of this structure in terms of the S parameters, in terms of its response, is the gap. So if you make a finer mesh on this region, you are supposed to get a better results in terms of S parameters. It's closer to the real world because you have a better sampling of the fields across a very important region of your coupler. That's it. Thank you very much.